Hello everyone, I'm excited to welcome you all today's webinar. We have incredible session lined up for you, packed with valuable insights, practical knowledge, and the key takeaways that you can start applying right away. Before we dive in, let me introduce our company. We specialized in technical reservoir studies, field development, reservoir statics, dynamic modeling, technical support for academic research, assist assistance in writing technical papers, publication, technical petroleum courses led by industry experts, mentorship programs, customized training solution tailored to your needs. We are pleased to introduce our esteemed instructor, Dr. Islam Ali. Dr. Ali is a senior geophysicist with over 16 years of experience in petroleum industry, specializing in exploration, reservoir characterization, and machine learning geophysics. He has authored more than 30 scientific publications tackling advanced geophysical challenges and contributing valuable insights to the field. His work has earned him multiple industry awards, recognized his innovative research and technical excellence. Beyond his technical experts, Dr. Ali is known for his exceptional communication and presentation skills, making complex concepts accessible and engaging. He is also proficient in English, ensuring a smooth and insightful learning experience for all. Let's give him a warm welcome.
Hello, and thanks a lot for your nice introduction. I'm very glad to be here with you today. Let me share my screen. Please let me know once you see the screen. You can see it? Perfect. Okay, so let's start right away. This should take like between 30 to 40 minutes, and then we can discuss the outcoming of the learning process. Um, any questions you have, any comments, just afterward. So let's start. Our topics today is about the application of machine learning for geophysical interpretation. So I think I don't need to reintroduce myself. The guy did a perfect job here. So let's go directly to the content. So we will cover three parts. So first part is the theoretical geoscience application of machine learning. And then we can move to the examples and case studies for machine learning in geophysics and in geology. And then we will have a very brief practical exercise just to digest and see how easily the theories and the application of machine learning can be done. So just let me start with this, I can say, silly question. Let me ask you. Imagine this scenario. Imagine that you have stock shares in a petroleum company, and this company is doing just fine. So everything is running smoothly, and you are gaining profit from this company. And then you heard from a trusted person that the gas price will go down in the next few days. And this is the best chance for you to sell out your shares. So this is the scenario, and my question is, what will you do with your shares? Will you sell it immediately or keep them, or just wait and see, or other? So I'll not receive an answer from you right now, but keep in mind, we'll get back to this question later at the end of the presentation. So let's start with the first part. What is the machine learning and what is the application of machine learning in the geoscience. Machine learning actually is a part of the biggest umbrella, the artificial intelligence. And as you may know, the artificial intelligence covers both the algorithms and the uh, hardware. So the artificial intelligence work with the software and hardware. The machine learning is this branch that covered the algorithms we use from the artificial intelligence. So what is the meaning of the machine learning? Machine learning simply is the field of AI that allows system to learn from the past data. So we need our systems to learn from the data we already have and then make intelligent decisions on their own. That means the algorithm should done the job without explicitly programmed. It will learn from the data and then transfer this learning into the new case. So imagine this, if you teach your machine, this is the apple, this is how it looks like, and this also an apple, this also an apple, and then you give it the chance to see a new apple, and he can recognize this is also an apple. It's different in color, but still have the same characteristics. So he can recognize from the data he already went through that this is also an apple. The same exactly we do in the geophysical field and in the geology. We teach the machine, as an example, we have porosity or saturation or any property, and we teach the machine this is how our property looks like. So he will gain this sort of learning and then apply it. So once he see the characteristics, it can recognize this porosity should be high, should be low, and etc. And there are many types of machine learning, and there are different classification styles for classifying the machine learning, but this is the common one. Types of machine learning could be divided into four parts. Supervised learning, and we mean by supervised, you teach the machine and they give it the answer uh, before it goes. I mean, imagine that you build a machine that can recognize the faces, just like your mobile phone does. So you will give it multiple figures, multiple pictures of human faces, and it can learn from this data, and then it will be able to recognize the faces for the human at the real life. So this sort of learning is called supervised learning because you would supervise the learning process of the machine. This can be used for classification and regression tasks. And by classification, we mean in the geology field and in the geophysics field, you can classify the data. That means you can use this algorithm to classify the facies, as an example, into sand, shale, limestone, and so on, or good quality reservoir and low quality reservoir. So this is the classification mode, and the other mode is called regression mode. The regression mode means that you will predict the actual value, the exact number of the porosity for each cell, or exact number of saturation, or for permeability. It will give you exact number. So this is the meaning of regression. So it can do both classification tasks and regression tasks. Second type is called unsupervised learning, and by unsupervised we mean that it can just take the data and classify them, cluster them, put them on classes. The class, every class will be meaningless unless you interpret the class and say this class belongs to sand and this class belongs to shale. But the machine just will do the classification, or it's called clustering. Just put every set of points in a specific cluster. Third type is called reinforcement. and learning. And by that, we mean the learning through the interaction and feedback from the user. And as an example, the ChatGPT and the DeepSeek works with this manner. It learns from you, from your interaction and your feedback. And there are other type of machine learning is called semi-supervised and self-supervised and transfer learning. These other specialized types, and these types could be reinterpreted under uh, one of the previous types as well. And before go to the actual case studies and application of machine learning, we have to understand that there are lots of algorithms that works with machine learning, from the simplest linear regression algorithm to the very sophisticated and complex algorithms such as deep neural network and deep learning. So to choose best according to our problem, if we do a simple classification task or simple regression task, do we really need to go to the deep neural network and advanced algorithms, or just linear regression and simple algorithms will do just fine in this case? So it dependent on the case we have. I'll give you some examples. So you can see here to the left-hand side, the cross plots represent the input data. Imagine that the red points belongs to hydrocarbon bearing sand, and the blue could be shale as an example. So I have here three cases. The lower one is simple. The shale points to the left-hand side, and the hydrocarbon bearing points to the right-hand side. So you can use any classifier that can separate the two datasets easily. Even the simplest one, the linear regression, will do good in this case. Uh, the second one in the middle is the hydrocarbon bearing sand surrounding the shale points. So it is hard for simple algorithm like linear regression or linear support vector machine to do the classification correctly. So you need, in this case, very advanced algorithm. The third one in the upper right and the upper left hand side, the a bit complex. The hydrocarbon bearing sand went through the shale unit. There is interaction between the two data sets. So linear will fail as well, but you need advanced algorithms such as decision tree or random forest, and so on. So what we look at here is a classification problem. You need to classify the points into hydrocarbon bearing and non-hydrocarbon bearing points. Another example is regression. So imagine that you have a property like porosity as an example, and you have input such as P impedance or inversion product, and you need to build a relation between them. So you have three cases. First case is very simple. You can capture this case with linear regression, and it will fit all points just perfectly, and it will do the job. Second case, the points is still at a trend, a bit curvy, but still following a trend. Last case is you have scattered points. So in this case, the linear regression will fail. You need advanced algorithm such as random forest or neural network. So as you see, it is very much dependent on the case you have. If you have a simple case, you can work with a very simple algorithm. The more complex case, the more advanced algorithm you need. Now we'll go to the actual real life examples that we use for neural network and the machine learning in general. So the machine learning applied in all parts of the subsurface data. First is seismic acquisition and processing. What we can do with the machine learning, we can improve the acquisition performance, and also we can reduce the noise during the processing using the machine learning. Let's have a look here. So for the acquisition part, imagine that your vessel is running and you need to run the vessel at optimal speed, and this speed will be subject to many factors such as the wave and the wind velocity. So you need to control to understand these factors and then adjust your vessel speed. So this case, you can see here this dashboard is running with the machine learning algorithm that can understand the effect of each of these elements and then adjust the speed to the optimal level. This is actual case present by BGS. Another case is from the processing, and the application of processing is very famous with noise removal. You can see here in the input data, there is some noise, and this noise you can see how it was removed in the lower part, lower left, lower right part after you apply the convolutional neural network, which is a deep learning algorithm. Unlike the conventional method for denoise, you can still see the effect of the noise running everywhere through the seismic volume. So it is very easy for machine learning algorithm to teach it. This is how the noise looks like, and I want it to get removed from the data, so it can do the job easily. And you can see here how it removed the data. Guys, you see my mouse, right? Okay. Now second example is seismic interpretation, and we use the machine learning in the interpretation for doing automatic interpretation. I mean, for horizons and for faults, we use supervised classification, something like support vector machine or decision tree algorithm. Here you can see the application of the machine learning, how it can be applied to do an automatic interpretation. You can see the black dotted point here is the manual interpretation versus the automatic interpretation that is done with the machine learning. We use here the k-means algorithm, which is unsupervised classification algorithm. We can do the interpretation using both supervised and unsupervised, but it will work better if you do supervised interpretation. As well as the faults interpretation, you can show the machine how the fault looks like here in this variance section, various map. And then once you teach the machine how the fault look like, it will do the job over the entire 3D cube. Then we can also apply the machine learning in the velocity modeling. So velocity modeling, we can do it in both in the processing through the seismic processing steps in order to build seismic velocity that is reliable. And also we can do it in afterward, after you do the processing. Once you have the data and you want to convert your data into depth domain, you can model the velocity using advanced algorithms such as neural network. Let me show you how it looks like. To the left-hand side, the normal velocity model, and you can see the gradational change in the velocity when you go deeper. And this sudden change belongs to a channel that's filled with hydrocarbon. And you can compare this with the velocity that's created with the neural network. You can see how the details in the seismic section appeared clearly. The lateral continuity is much better, and you can even see through the channel the different geometries and the different parts of the channel. So you can see every small change in the velocity profile that's captured by the machine learning algorithm. And this is very helpful for the subsequent part, which is the pool pressure prediction and geohazard identification. And by that, we mean we want to predict the pool pressure for the formation that we will drill through in order to identify any possible geohazard, such as gas pockets that may be overpressurized. It needs to be detected before you do the drilling. So in this case, you can see also to the right-hand side, the deep learning, how it successfully can detect the gas pocket and the overpressured parts. This is very helpful to identify where you can put your well to avoid any possible hazard. And also it will help in mitigating any possible kicks that you will face during the drilling. Next part is the application when you do prospect generation and maturation. So this will work in the exploration phase. So in the exploration phase, you don't have wells. So most likely you need to identify the possible prospects, and you will do this without supervision. So you will work with machine learning in the unsupervised mode. So we can use something like self-organizing maps. This is unsupervised machine learning algorithm that can put every part of the seismic in a cluster, and then you can interpret these clusters as this map. You can see here the blue represents coral reef. So in this case, this is our prospect. The same here. This is unsupervised learning with k-nearest neighborhood. Example, you can see different fishes here. And once you drill, you can assign every fishes with this. So you have here in this section three faces or four faces: the blue, the green, the dark green, and the yellow one. And this section also show four faces, and these fishes were interpreted as dolomite, limestone, sandstone, and shale. So this is completely unsupervised classification, and this works well in the phase of exploration. Next part is very important, and it is implemented through the development stage, which is called reservoir or seismic reservoir characterization. So in this phase, we use the machine learning in order to understand the reservoir properties, such as porosity, permeability, water saturation, and facies. So we have wells, so we can do supervised machine learning. So we can use it to enhance the inversion process, and this is a comparison between one of the inversion that is done with a conventional way in the middle, and then the lower one is an inversion that is done with the help of machine learning. And you can see in the maps the reservoirs in the middle, the channels in the middle, appear very clear in the machine learning supported inversion, unlike the upper one, which is you missed here completely the reservoirs in the middle, I mean. Alternatively, you can use the machine learning to do an inversion. So it can stand alone and produce the same inversion products. It can produce P impedance, shear impedance, and density. You can produce them all from the neural network, not from the inversion. So it can stand against the inversion, not only help the inversion to get better, but also it can stand against the inversion and give very good results. As you can see here, the comparison is very comparable between the two products from the two methods. Also, you can skip completely the inversion and just bring the seismic with its internal attribute and predict the reservoir property directly. The example we see here, we have used the seismic and its attribute in order to create water saturation 3D cube. And you can see here the comparison between the actual well that was drilled after we did the study compared with our predictions. The very good correlation between them. You can see here the effect of the hydrocarbon, and again, it's the colors, which is the prediction from the machine learning. In this case, we used probabilistic neural network algorithm. Another very important usage of the machine learning is enhancing the reservoir modeling process. So conventionally, we use the input data, I mean the horizons, the well data, and the seismic, and build a static model and go to the history match and dynamic simulation. So you will go through many process. First, you have to build structure model with the 3D grid in time domain, and then you will have to distribute the facies. So you do facies modeling, and then you have to distribute also the petrophysical properties, I mean the porosity, permeability, and saturation. So you have to do this petrophysical property modeling as well. And then put different scenarios and uncertainty analysis. So this is the end of static model, and then you go to the dynamic model, the simulation in the grid. And then we compare or with actual production. This process is called history matching. So if the history of the production is not consistent with your predictions, you have to go through the process all over again. This process is very long. It takes months, and it's very demanding process. Machine learning will shorten this process and make it much shorter and more efficient. How? You will bring the inputs directly to the machine learning algorithm, in this case, the neural network, and then predict the reservoir properties in a 3D domain. And then you will take these reservoir properties directly to the simulation and to the dynamic model, and then do the history match. This is much more efficient procedure. So machine learning enhance dramatically the reservoir modeling here. Now let's go to the practical part. Uh, I put this practical part here to show you how easily you can implement the machine learning and get a product very quickly out of it. So in this part, I'll do porosity prediction with machine learning using Python coding, Python programming language. So Python is a very easy language. I mean, according to the programmers, they put it as the easiest language, programming language. So we'll use Python. It's a very machine learning friendly language. So what is the aim of this exercise? Imagine that you have density, sonic, and gamma ray logs, and you want to create from these logs a porosity log. Imagine that you know nothing about the petrophysics and you just have the task that you need to predict the porosity. So I need to build relationship between these three inputs and my output, the porosity. And then once the machine learn how to produce porosity from these inputs, it will apply the same formula to other wells and create porosity for every well in my field. So it's a simple task, but we have to understand what we have to do. First, we have the last file. The last file is the standard format of the logs. You have header here, and in this header, you have the information of the wells, the information of the logs. You can see here our logs in this header. And then you have the log reading itself. We have here many columns represent these logs. Okay, so what I have to do here, I have to understand first what is required to be coded. I have my log in the Google Drive. So I need first to read it from Google Drive in a LAS format. This is the format of my logs. Then I need to clean the data. Why? Because the data will have readings like you can see here. The first reading starts with minus 999.25. This means this data is null. There is no reading here. So I need to get rid of these readings because it means nothing. It's not real reading. It just means null data. Then I need to do what is called feature selection. We'll go to this part and understand what does it mean, and also the standardization. And then I have to train the model. I choose, and I mean by this, the algorithm. I have to choose the algorithm to apply it here. And then my prediction and the evaluation have to be done and plot the result. So I have many parts I have to write in my code in order to run it on the last file, and then it will predict the porosity and plot the result. But during the last 2 years with the ChatGPT and DeepSeek, this task is very easy one. So I go to the ChatGPT and just write this sentence. First, I need Python code using Google Colab. That's because I prefer to work on Google Colab. We can discuss this later. To load the last file from this directory, the directory is on my Google Drive. And then I wanted to remove the null values, which is minus 999.25. And I want to use phi effective. This is the effective porosity as y. This is my target. And use the ρ delta t and gamma ray logs as x data. So this will be the input, and my target is to predict the porosity. And I want to do standardization, and by that we mean that I ask the ChatGPT before running the algorithm to make the data at the same level. I mean, look at the data we have here. You have porosity range that is different than the delta T range, that's different than gamma ray range. That is, of course, will be different than the porosity ranges. So I want all the data to be at the same page. So I will do the standardization. They will all be running at the same ranges. Okay, let's go back to the ChatGPT. We'll ask it to train the X data, the inputs, to predict the Y data, our targets, using 3 algorithms. Why? Because I want to compare between them. I will use a very simple linear regression and 2 advanced algorithms. One is called random forest and one is called neural network. And I asked ChatGPT, after you did this, plot the actual porosity log with the depth to be plotted as a log, and then put over it the predicted porosity log from each algorithm, but put it alone. So each plot separately. Okay, so this is the prompt I'll put in ChatGPT. And right away, ChatGPT will create a full code that's functional. So once I put the code on my notebook reader, the Google Colab, and run it, it will do the job. Sorry, can you mute the attendees? Thank you. So as a result of that, you can see here this code. This code is the one generated by ChatGPT. I just put it on Colab notebook, and this is the result here. You can see the code and you can see the result plotted as well. We'll go through this code in order to understand it better. So in the first step, it creates these lines in order to read my lathe file from its bus, from the G drive. And also it loaded here what's called libraries. So these libraries are important in order to do the job. It has already saved codes, so it will shorten the time. Then in the second step, it put this line in order to drop the unvalid values, minus 999.25. It will drop these files, these readings from my files. And then it will use as X the 3 logs, the density, the sonic and gamma ray, and it will use as target the porosity. And then with these 2 lines, it will do the standardization. Then in the next, it will apply 4 algorithms, 3 algorithms, linear regression, random forest, and the neural network here. So these 2 lines for each algorithm. Then we will make the predictions with these 3 lines. So it will do the prediction for each algorithm with a single line of these. This is the prediction for linear regression, the prediction for random forest, and the prediction for neural network. Then it will compute the R square. R square is the correlation coefficient. How good is my prediction is, and it will calculate also the error. Then here it's a long a bit, but this is the plotting. So each part of this will plot the prediction versus the actual porosity. This is how the code looks like, and this is the result from the linear regression and from the random forest and from the neural network. And you can see in every case, the black is the actual log, and the red, green, and the blue lines are the predictions. And we have here perfect match, 99%. And you can ask also ChatGPT to describe the code, what it did for the code. So it will describe each part of the code. I did this to do that. Okay, so till now we work on what so-called the back end. work with the codes, but we can also make an app out of it. So I'll ask ChatGPT to convert my code into UI. UI means user interface, using this one, TK enter. So it will create something like this. So this is actual program. The extension of this is .exe. So you can create a small program here. In this program, you can do the same job we just did. You can load the data, you can train, and you can predict and plot the result. And also you can add an icon for export the model or to load the new data and apply the same. Okay. So let's back to our question I asked you at the beginning of this presentation. Imagine that you already have a stock share in a petroleum company. This company is doing just fine, but you heard from trusted person that the gas price will go down in the next few days, and this is your chance to sell your shares. What will you do in this case? You have four options. You can sell immediately, or keep them, or wait and see, or other option. For me, I'll go for other. Why? Because we have data, and this data is not just exploration and drilling. You have also data from production, from storage, and from export and import data. And based on these data, you can take it and just write a few lines of coding, and then you can create, with an advanced algorithm, you can create gas price prediction. And so you can compare it with the actual market and then predict ahead, will the gas price go up or down. In this case, you have accuracy that exceeds 90%, so you trust on it. This means less risk and less and better decisions, and also it will save millions of dollars. So as a summary, the data analysis is one of the advantages of machine learning, because we can process and analyze large volumes of geophysical data, and I mean the seismic data, the log data, and other related geophysical data. And this means money. This is very cost effectively approach. I mean, the machine learning can significantly reduce the cost of either exploration or development. Also, machine learning is much better in the accuracy and the precision, and you saw many examples of how we can enhance our data and using the machine learning advanced algorithms. And this means also automation, because you saw we can create in a few minutes an app that do the job automatically. So automation is very, very positive point of the machine learning. Okay, thanks. And this is from my side, and I'll open the floor for any questions you have. Thank you.
Thank you, Dr. Islam. Anyone have a question?
Hello, assalamu alaikum. Hello, everyone. Hello, Dr. Islam.
Hi.
Great presentation. Thanks a lot, Dr. Islam. Nice work. I just have a few thoughts. You mentioned a couple of things. First, you have preference of using, I'm going to talk about the IDE that you are using. And basically, I have three angles here, three items. If you could share your expert opinion on them. The first one is more related to the IDE. The second one is more related to the software applications. The third one is more like trendology and future applications. So let me start up with the first item, which is the IDE. You mentioned, I'm sure you're using lots of, editors for writing code, but you mentioned you prefer Jupyter. I use Jupyter in all these ones, but the thing is, as you know, Jupyter also has limitations, has pluses, but lots of minuses. For instance, I use Jupyter all the time and Charm, but Jupyter is my preference. The collab or the Jupyter collab, I use Spider. Spider is my preference because I can write one code. I can chunk it into pieces and run whatever piece I want. So I want to ask you on the use of the different IDEs. Are you still in favor of using the Jupyter or the Colab? This is one thing, one item down. The second one, software. There are tons of softwares right now. And when it comes to sizing, I'm geophysicist. Sorry, I did not introduce myself. But as geophysicist, if you use, for instance, AspenTech, in that paradigm software, the size Earth, within the 3D canvas, they added tons of some very good machine learning stuff, and you can generate properties specifically for porosity fascias, and you name it. Also, for many years, since 2005, I guess 2004 and 5, when I was at University of Calgary doing my degree, I had the pleasure to get to know in our research Dr. Brian Russell, and he gave me the software, Russell, where you have emerge and you can predict within the probability neural network, default neural network, and the multi-attribute. So there are tons of things, and they keep on adding every once in a while some additional things. So I want your thoughts on the different software applications where you implemented it specifically for some complex cases related to carbonates. And the last one, where do you see we are headed? So I'm sorry that I was long on my thoughts, but if you can sum it up for us for all these three items, I really appreciate it. Thanks a lot, Dr. Islam.
Thanks a lot for your very insightful comments. So starting with IDM, I mean the one I work on it, I use it nowadays is Google Colab, and I use it because it offers additional features that is not in the Spider, such as it give you free space in Google, and also it give you powerful machine, so you can access to what is the called TPU. TPU is tensor processing unit. It will give you like 300 RAM, gigabyte RAM. So this is very powerful machine. You have access to it free. So you can use it in heavy machine learning process. So nowadays I'm using Google Colab, and they did good job in the machine learning process. This is for the first part. For the second part, you speak about the software. Yes.
Yes, sir. But if you can mute the other participants because I cannot understand. Can you mute the others, please?
Yeah, if the coordinator can mute, please. Okay. So now go back to your question about the software. I'm a big fan of Hamster Russell actually, and I use it a lot. The emerge module for producing reservoir properties from neural network. But as you know, it doesn't contain all the algorithms you need. I mean, as example, it doesn't contain random forest or decision tree or XGBoost or other advanced algorithms that we use currently for the classification, especially. So unless you have these algorithms in a software, you have to do it through the coding. But if it's available in the software, I strongly encourage everyone to do it through the software, of course, because the software will decrease the amount of time needed for anyone to do the job. But also you have to consider that how much you're gonna pay for the software. So all what we did here is free. You can do the inversion prediction the 3D reservoir property prediction with additional steps. So you have to go to a free software like OpenDetect and create seismic attributes, and then go back to the Google Colab and code through Python, and then go back again to the OpenDetect to load the result. So it's more steps, but it's free eventually. So it's up to the person if he can offer the software price. It will be better to do the job in a few steps rather than spend much time in doing this. Your last question was about what? Sorry, I forgot.
Yes, the last question was more like the terminology. Where do you see the application, where we are headed, and if you plan to arrange a couple of sessions just to show us either through the coding of some seismic or graphic or some data, some more geophysical data, if you have any plans, just to show us all these interesting algorithms. And where do you see it fits right now, especially for more carbonate reservoirs and complex structure? If you have successes, if you have concerns, in general, the trends and where we are headed. Thank you, Doctor.
Thanks a lot. 2 years ago, I was aware of somehow I have a vision of where the industry headed, because the machine learning is emerging trend in the oil and gas industry, but the growing is slow. As an example, the Betrel just start implementing the machine learning in the automatic interpretation this year. So they spend a lot of time, and the results just appear now. But with the revolution of ChatGPT and DeepSeek, and how easy you can nowadays create a full code without even knowing what the code is talking about, uh, I don't have answer. I don't know how the industry will act in the next days, but I'm trust that machine learning will play a very important role, and the geoscientist who's knowing how to implement machine learning will have a lot of advantages over other ones who don't have. And it will be my pleasure to discuss with you in the future anything regarding to the carbonates. I have a few examples that I work with it, and it give good results. So we can discuss it in the future, inshallah.
Inshallah, pleasure is mine, Doctor. You're awesome, and I would love to continue discussing with you and for maybe future collaboration. Right now, I'm kind of semi-retired, and I'm based in Canada, but right now I'm visiting the Middle East, and I would like to share some of the thoughts and some of the work. Maybe in the future, if you have planned to participate in workshop conferences, maybe we can huddle in and do some work together, either coding or use some application, whatever you feel more comfortable, if time allows both of us. That would be really awesome. Thank you so much again, Dr. Islam. That was great from you.
Thanks a lot. The pleasure is mine. Thank you.
So anyone have any question again?
We have a few questions in the chat box. So I don't know if this is something different, or we just discuss these points. Okay, so I have questions from Mr. Muhammad Qasim. It's not useful practice. You must have to select feature basis on some algorithm. Sorry, I don't understand what you are referring to.
Hi, Dr. Islam.
Hi, Mr. Muhammad.
Sorry, I didn't address my question properly in chat. I mean that we must have to adopt some algorithm to choose our features. You
Mhm.
directly choose features like density and things like that to produce velocity.
Mhm.
We must have some features in log file. We have a lot of well logs. So based on some algorithm like decision tree or random forest, we choose the best features. You just choose two or three features. I mean that we must choose features based on some algorithm.
Yes, yes, I'm 100% with you. And this is a standard when you are using seismic attributes. As an example, you have full list of seismic attributes. You don't know which one is best, or which set of attributes you will use. So you use something like random forest, as you mentioned, in order to select which is the best attributes for you, or which is the important set of attributes that you will use, and then assign these attributes to be X data and versus your Y or target data. Yes, you are correct. But in this case, we have only three logs, and these logs are important to derive porosity. So if you do here the feature selection, uh, you only have three inputs. So it's not necessarily to, uh, neglect one of them. But in other cases where you have much data, yes, you're correct. You have to select. Do the feature selection and select the best attributes.
Thank you, doctor. And one thing more. We don't have any evaluation criteria for your prediction. What do you say about this? There is no statistical parameter that is describing the relation of our target and predicted values.
Okay, so my preferred uh, algorithm, or my preferred approach to validate the result. If I'm doing a 3D job with seismic, so I'll use a blind test. So first you do the cross validation to investigate the validity, especially when you do neural network. You have the training versus the validation data, so you can see actually how it goes. And then you have blind tests. Some wells you keep away from the study, and once you finish the study, you will put these wells and predict and see the prediction versus the actual data. And this will give you very important indication of the quality of your predictions. And again, in this case, we just use one well with three logs. So you cannot really measure the quality with the same well. You need much data, or other wells, in order to do the cross validation and see the accuracy of your predictions.
Thank you very much, doctor.
Thank you, Mr. Mohammed. We have a question from Ahmed Fahmi asking about how easy applying machine learning on 3D volume on Python. Uh, well, it takes a few more steps because 3D seismic need a different library to be used, such as SigY.io. But yeah, you can do it eventually. So I have a few videos that describe the whole process. Since you start from OpenDetect and export the volumes to Python and do the code in Python, and then create a 3D porosity volume and put it back in OpenDetect. I have these videos on my channel, but unfortunately they are in Arabic. So I think you can go back to these videos. They are helpful. We have a question from Abdul Hakim. who's graduated from petroleum geophysics, and he's asking about the job market. Okay, and how will AI and machine learning will impact on it. Okay, so my answer is it's very important, and in the next few years, I think it will have a great impact if you are a geophysicist or a geoscientist in general and can really understand the machine learning and AI, or you cannot understand it, and it's important in the industry. So anyone who's geophysicist or a geologist and willing to enter the industry, I'm encouraging him to understand at least the basics of machine learning, because it will play a very important role in the future, in the near future, inshallah. Okay. Do we have any other questions? Okay. Okay, thanks a lot, Abdelhakim.
A huge thank you to you, Dr. Islam Ali, for these insightful explanations and the valuable discussion today. Your expertise and deep knowledge have truly enriched this session, providing us with practical takeaways and greater understanding of the subject. We sincerely appreciate your time and effort and dedication to sharing your knowledge with us. It has been an incredible informative session, and we look forward to learning from you in the future. Thank you once again, Dr. Islam. Thank you everyone for attending our webinar. Don't forget to subscribe to our channel so you can watch the video once it's uploaded. Thank you again, everyone.
Thank you. Thank you a lot for hosting me. Thank you.